So let us look at what the Prim's algorithm is. What Prim's algorithm says is we start by selecting a random vertex on our arbitrary vertex from the graph. Now it's actually generally the vertex which has a least cost. Then there is a set A we maintain which stores the edges of the graph which forms the tree. And at each stage, what we do is we select the next minimum cost edge such that the tree which grows is a connected tree. So we select an edge u comma v which is not already there in the set A, that means which is not already there in the tree, and we merge the set u comma v, we merge the edge u comma v in the existing set A of the edges of the tree, spanning tree. Now when we merge it, it should also form a tree. What this means is the edge whatever we are going to select, next minimum cost edge whatever we are going to select, that should not form a cycle again. It should be a tree. So this process of selecting the next minimum cost edge and all continues till we explore all the vertices of the graph, and all the vertices of the graph is present in the tree. That is what was the one of the property of spanning tree. That is, all the vertices of graph will be there in the spanning tree, and that too connected. So, I mean, an informal algorithm would be, a Prim's algorithm would be, to repeat these steps of finding the minimum edge and minimum that to connecting A. So, once we select an edge, when we select a vertex, endpoints, two vertices of the edge, the next edge which we select should be minimum, and that should be connecting to A, connecting to the tree. So tree should be, as tree grows, it grows in a connected manner. And then union the edge which we have selected. This repeat until all the vertices are there in the tree or in a set of edges. Now let us practically look at how this Prim's algorithm works. Let us consider the graph on our right hand side. This is the graph with 7 vertices and its respective edges, and each edge has got a cost. Now a spanning tree T, we're going to construct a spanning tree using Prim's method. So spanning tree T, initially the set A, which is a set which contains the edges of the spanning tree, is null. Initially it's null. Then let us consider we are selecting vertex A. Once we select vertex A, what is the minimum cost edge actually from the graph? It's 10. And 10 is with vertex A. So let us assume that we select vertex A. Vertex 1. And 10 is the minimum cost edge. Now this vertex 1, which has minimum cost edge 10, connects vertex 6. So what we do is we select this edge and the vertices with it, and those that edge is placed in the spanning tree, and we union the edge u comma v, that is 1 comma 6 in set A. So set A now will be containing an edge 1 comma 6 on vertex 1 to vertex 6. Then what we need to do is we need to select next minimum edge, not among all edges. The next minimum edge is 12, but next minimum edge not among all the edges. Next minimum edge connecting A. What is A? 1 comma 6. So connecting 1 comma 6 and which is not in A. So which edge is connecting 1 comma 6? Connecting 1 comma 6 means connecting 1. there is an edge between 1 to 2 which connects 1, and there is an edge between 6 to 5 which connects 6. And remember, 1 comma 2 is an edge where 2 is not in A, vertex 2 is not in the set A, and vertex 5 is also not in set A. And who is minimum among these two? 28 or 25? 25 is minimum. So we select the edge, minimum edge, u comma v. Here u is a vertex 6 and v is vertex 5 to a vertex not in A, connecting, and not in A. 5 is not in A. So we select this edge and create a spanning tree, and then put 6 comma 5 in the set A. Merge it, union of that. Now next, what do we have to do? Find minimum edge u comma v connecting A, that is connecting 1, connecting vertex 1, vertex 6 and vertex 5. What all are the vertices connecting 1, 6 and 5? What all edges are connecting 1, 6 and 5 vertices? There is an edge 1 to 2 which is 28. There is an edge 5 to 7 which is 24, and then there is an edge 5 to 4 which is 22. So this edge 22 connecting vertex 5 and vertex 4 is minimum. So we select that edge and grow the spanning tree. That edge is placed in the set A of edges. Again, we have to select an edge connecting A, that is connecting vertex 1, vertex 6, vertex 5 and vertex 4. What are those edges? We have edge 24 connecting 5 and 7, edge 4 connecting edge 18 connecting 4 and 7, edge 12 connecting 4 and 3, and edge 28 connecting 1 and 2. Which edge is minimum among this? Edge connecting 4 and 3. So we put that edge in the spanning tree and then add that edge to set A. Next, we have to consider now minimum edge connecting A, that is connecting vertex 1, vertex 6, vertex 5, vertex 4 and vertex 6. So there is an edge 28 connecting 1 and 2. There is an edge 16 connecting 2 and 3. Edge 24 connecting 5 and 7, and edge 18 connecting 7 and 4. Which is minimum? 16. Edge with cos 16 is minimum. So we select that edge, put it in the spanning tree and union it with the set A. Then what is the next? Now next minimum edge connecting A is from 1, 6, 5, 4, 3 and 2. So these are the edges, and among these edges 28, 14, 24 and 18 we have an edge 14 which is minimum. So we select that edge and put it in the spanning tree, and that edge is added to A, set A. Now should we proceed further? No. If we proceed further, we will be creating a cycle. So therefore we will not proceed further. Why? Because all the vertices are in A. You see the set A, all 7 vertices are there in set A. And the Prim's algorithm terminates, and we have the minimum cost spanning tree. Definitely Prim's algorithm, using this procedure, we will get a minimum cost spanning tree. Now what we have to see is, we have to select, remember we need to find the minimum edge connecting A to a vertex not in A. Now if we consider, let's say next minimum edge would be 18 because we are left with 28, 24 and 18. Next minimum edge will be 18. Assume all vertices not over, assume that. Now 18 is an edge between vertex 4 and 7. So can I add this vertex to 4 and 7? If I add, it will create a cycle. Then how am I protecting the spanning tree from having cycles? The statement is connecting A. Here, the statement in the algorithm which says connecting A to a vertex not in A. This prevents us from creating a cycle. Why? Because if you select this edge from 4 to 7, now look at here. Both 4, vertex 4 is in set A as well as 7 is in set A. So when both the vertices or both the endpoints of an edge, both the vertices of an edge are in set A, then do not consider that edge, discard that edge. If you consider, it will create a cycle. So if both the vertices endpoints of an edge are in the set A, which is a set of edges of the spanning tree, then discard that edge. So this is how Prim's algorithm works. Now let us look at the time the cost of the Prims. That is, what will be the cost of this spanning tree created by Prims? Sum up all the edges, and here we get the cost as 99. Now let us try to look at the actual algorithm. What we have seen is a informal it's like a descriptive Prim's algorithm, but actual implementation is done using a pseudocode, and this is the Prim's algorithm. What we have is the Prim's algorithm takes 4 parameters, that is E, which is a set of edges. Cost is nothing but it's a cost adjacency matrix where all the costs of edges are stored. N is the number of vertices, the third parameter, and T is an array, 2-dimensional array, which contains 2 columns, only 2 columns. The first column, we store the vertex, the first vertex of the edge, and second column we store the destination vertex of the edge, the second another vertex of the edge. And this T array, 2-dimensional array T, which has only 2 columns, actually stores all the edges of the spanning tree. That is nothing but this T array is the set A, which we have seen in the previous example how we solved it. The very first statement, let K and L be an edge of the minimum cost in G, that is in E. That is, among all the edges, select the edge with the minimum cost. That is arbitrary, we are trying to select a vertex and with the minimum cost edge. So let's say K is vertex 1 and L is vertex 6. Now we will have a variable minimum cost, which is the cost of K comma L, because that's the only edge right now between vertex 1 and vertex 6. So we assign it to minimum cost. Then T, I said it's an array, 2-dimensional array, where first column is the source vertex, that is K, and the second column will have L. This is not 1, this is L actually, L. So L is vertex 6. So T is the array which will be storing the edges, and right now we have edge from vertex 1 to vertex 6. So vertex 1 to vertex 6. Then we use a for loop, this for loop from line 5 till line 9. This for loop is used to actually assign the values to another array known as near. So we will be maintaining an array near. The size of this array will be number of vertices, and the index of the array will represent the vertex, actual vertex. The near array actually will be having value 0 if the vertices are already there in the spanning tree. Else it will have some other value. Now, if you just try to solve these statements from line 5 to line 9, we get near of 2 as 1, near of 7 as 1, near of 3 as 1. Because if there is no edge between 1 to 7, or there is no edge between 1 to 6, 1 to 3 actually, no direct edge I'm talking about, then it's taken as infinity. So cost of infinity less than infinity will be, it's false actually. So I value will be assigned K, which is in this case 1. So a near of 2, near of 7, near of 3, and near of 4 will be assigned 1. If if you solve this. And near of 5 will be assigned 6. That means near of 5 means near of this vertex 5. Which vertex is near to this vertex 5? Vertex 6. Now obviously vertex 7 is also near, vertex 4 is also near, but near at the first instance is near to the vertex of the spanning tree. So right now we only have vertex 1 and 6 in the spanning tree. So the vertex 5 nearest is 6. So if we include this, we will be growing the spanning tree. Then even in case of near of 2 is assigned 1, because this is because, though obviously 7 is also near to 2, 3 is also near to 2, but at this stage spanning tree only has vertex 1 and vertex 6. So near vertex of 2 is vertex 1 and near vertex of 5 is vertex 6. This is because to grow the spanning tree, to have the spanning tree, grow the spanning tree in a connected manner, in a connected way. Then as I told you, the near index, the vertices which are there in the near array, which are there in the spanning tree, their near value will be 0. So since K and L are the two vertices which are right now already been selected, K and L, and which will be there in the spanning tree, so we assign 0. So that's why 1, vertex 1 will be, the near will be 0, vertex in near will be 0. Then from line 11 till line 19, what we do is we iterate, that is each stage, what I said. At each stage, and this for loop runs from 2 because first edge we have already computed and put it in the spanning tree. And for n vertices, I told you there will be n minus 1 edges. So that is why for loop will run from 2 to n minus 1. And at each stage, at each iteration, we select a vertex which is not in A. That is near of J should not be 0. If it is 0, some vertex J, we select some vertex J, which is an index. I mean, index is representing the vertices actually in this algorithm. So near of J, near of that vertex should not be 0. That means if it is 0, that means that vertex is in the spanning tree. If it is not 0, that means it's not in spanning tree. And cost of that vertex with the near J is minimum. So if you look at this first step, cost of, let us say 2. So cost, let's select J as 2. Cost of 2 comma near of 2 is 1. So 2 comma 1 is 28. And cost of J is 5. Let's say J is 5. Let J be the index such that this is not 0. So J is 5 and cost of 5 comma near of 5 is 6. So cost of 5 comma 6 is 25, which is minimum 25. So that is why we are selecting this edge. Now this edge J over here will be 5. Now you can have for I equal to, so J can be anything else, or J can also be 4. But 4 of 1, J of 4 is not null, then 1 comma 4 will be infinity. It's not minimum, it will be infinity. So at this stage, when this J is selected, it is selected such that the vertices are near. That's what it picks up. The minimum, when we say cos J comma near of J is minimum, that means it selects the edge which is a minimum to the already existing vertices in the spanning tree. So now once we select J, we assign J to the set of array, the array T, which consists of set of edges in the spanning tree. So first column is assigned J, second column is assigned near of J, because near of J is 6. So there is going to be an edge between 5 to 6, vertex 5 to vertex 6. Then the minimum cost is incremented with the cost, appended actually, not incremented, appended with the cost of 5 comma 6. And then near of J becomes 0. What is J? 5. So near of J becomes 0. That means we have added that vertex 5 in the in the spanning tree and created an edge. Then we have another for loop. This for loop is for from line 16 to line 19, or line 16 to, let's say, line 18 actually. Line 16 to 18, this for loop is used to update the near array. Update the near array after selecting vertex j and putting it in the spanning tree. So what we did here from line 5 to line 9, same thing is done here. But we only consider the vertices which are not in the spanning tree. Only those vertices near value will be updated depending upon what the cost is, which one is minimum. So depending upon that cost, it will be updated. And finally, min cost is returned. Now remember, whether you try to trace this algorithm or not, or whether you try to work this algorithm, or whether you try to understand, or if you don't understand this algorithm. This algorithm is very important. You by heart this algorithm, because several times this algorithm has been asked in the exam. Now nobody is going to ask you to explain this algorithm. I explained you so that it will be easy for you to remember. And I explained you to show how this works. So this for loop will work for n minus 1 times. All the near values will be updated and all the vertices will be considered and added to the tree. And finally it is returned. So this algorithm is very important. You just have to by heart this algorithm, whether you understand or not. Now, let us analyze this algorithm, time complexity. Now this first statement, that is let KL be an edge of minimum cost in E. The statement is very simple, but what we have to do is we have to sort it, or we have to search. Search the easiest way is to search all the edges to find the minimum cost edge. Searching edges means if there are E number of edges, then obviously for every edge we need to repeat, we need to search. So this statement, first statement, will be taking O of E as the time complexity, where E is the number of edges. Then this for loop will run for n times, where n is the number of vertices. Then the statement within the for loop at line 11, let j, does the same work what the line 3 does, and it takes O of n. Now here we are saying n because n number, we search not the set of edges, we search the near array whether it is equal to 0 or not, depending on that. So let n be the number of vertices, so it takes O of n time. Then this for loop will also take O of n times to execute, so that the near array is updated. And these two, let j be index line 12 and line 16 to 18. These statements are within the for loop, and this for loop itself is running from iterating from 2 to n minus 1. So it takes O of n. Now since this statement takes O of n, so ultimately the line 12 statement and line 16 to 18 statements will be taking O of n square and O of n square. So O of n into O of n is O of n square. So this Prim's algorithm, entire algorithm, will be taking O of n square as the time complexity, where n is the number of vertices. So this is what is the Prim's algorithm.